Okay, good afternoon, everyone. I think we can get started. There will be anyone else who might wish to join us. Surely they will find we will have gotten started. So, like I told your friends, you guys and I are not meeting for the first time. We have met a number of times before. And once again, I have been assigned this particular component that I have to teach you. The component is in two parts. The first part is focused on intermolecular forces and phase equilibrium. Then the next component, we are going to talk about it when we get to that part. And luckily, we have 3 weeks that we have been given. And we are hoping that within the 3 weeks that we have of learning, we should be able to complete everything that needs talking about. Should we not manage to cover everything, we will still find time outside of the normal arrangement, or rather the normal duration that we have been given for this particular component, and make sure that we cover whatever it is that is going to remain, just like we did for the previous topics that or components that I taught you guys. So to get us started, let me just admit a few more people that are trying to join us. So, yeah. So to get us started, we look at we would like to establish what a phase is, intermolecular forces and phase equilibrium. So we see that the term equilibrium keeps popping up every time that we have something that needs looking at. So what is a phase? A phase is or can be referred to as a homogeneous part of the system in contact with other parts of the system, but this is separated from them by a well-defined boundary. That is how we can define a phase. So on the right bottom corner of the slide, we see that we've got this particular substance that exists in two phases. The dihydrogen oxide, which is commonly referred to as water. So it exists into two distinct phases. One phase is the solid phase, which is ice, and then we've got a liquid phase, which is water. Okay. But before we go into details talking about these things, by the way, I'm going to try to be as slow as I possibly can be, because there were concerns from some of our colleagues that because of poor internet connectivity, when I try to be a little bit faster as I'm explaining things, some of our friends were not able to follow. So we will try to be as slow as we possibly can, bearing in mind that that might slow us somehow, and we might have to look for extra time for us to be able to cover whatever that might remain at the end of the day. And I would like to point out to you that if you have something that you might want to say, do not raise your hand hoping that I'm going to be able to see your raised hand. I may not be able to see it because I'm using my phone and I have to navigate between softwares for me to be able to see what is happening in the group there. So just unmute and call out to me and I'll be able to attend to you. Okay, so we look at the characteristic properties of gases. We know that for gases, we don't have a defined volume and we don't have a defined or fixed shape. The gases tend to have low densities and they are very compressible. Their particles are able to move freely. For liquids, they've got a defined volume but no defined shape. They take up the shape of the container in which they have been put, and their densities are quite high and they are only slightly compressible. Their particles slide past one another freely. For solids, we've got defined volumes and defined shapes. Their densities are quite high and they are virtually incompressible. You can't really compress them that much, and their particles vibrate about their fixed positions. So you probably are wondering, but these things we already know them. Why are we looking at them? Well, there would come a time when I will remind you to say, you remember the properties that we had looked at, which we had tried to review about gases, liquids, and solids. So at a later stage, we're going to have to try and explain why some substances exist as liquids, others exist as you have solids, and also you have those that might exist as gases. So we will use the information, the knowledge that we are going to acquire from this particular part of the component of intermolecular forces to try and explain why those substances exist in those states. Okay. We have this particular slide that tries to break down intermolecular forces versus intramolecular forces, and it's going to try and show us how we can measure their strength. Okay, so in terms of how we define these forces, intermolecular forces, these are referred to as attractive forces that exist between molecules. So we might try and think of them as the glue that is holding the separate molecules together in liquid or solid water, as per the slide that we are looking at. So examples of these types of intermolecular forces that we have, for instance, hydrogen bonding. So hydrogen bonding is an example of intermolecular force. We can also think of dipole forces of interaction, something that we are going to look at in more details at a later stage. So those are some of the examples of intermolecular forces that might exist when you've got two or more molecules of a substance. For the intramolecular forces, you're looking at forces that exist within a molecule, and these forces help to hold the atoms together. So an example of an intramolecular force is covalent bond. So covalent bond is an example of an intramolecular force, and you have these forces existing when you've got say oxygen hydrogen bonding. So the two of them are bound to each other through this type of an intra molecular force. So whenever you think of intermolecular, you should think of forces that exist between molecules or amongst molecules. Then intra, it is within one molecule. But how strong are they, these forces that we are talking about? So when you look at this part of the slide here, you've got a comparison between the two of them. For water molecules, if you add one more of water, for you to separate the individual molecules of water, one from the other, you might need the amount of energy equal to 41 kilojoules of energy. If you were to try and attempt to break the bonds, okay, the bonds between the atoms, between one atom and the other, the amount of energy that you'll need to break the bond between oxygen and hydrogen, for instance, will be equal to 930 kilojoules of energy, quite high compared to what you might need just for you to separate the molecules one from the other. Okay, so this then leads us to what parameters would we have to use for us to be able to measure, say, intermolecular forces? These are the forces that exist between any two given molecules of a compound. There are a number of things that we need to consider when doing this. So let me just admit someone who is trying to join us. All right. So we have a number of parameters that we can use. We can use boiling point, for instance. So boiling point refers to the amount of energy that is needed to pour molecules into a gas. So you're trying to separate the molecules and change them into a gas. So the amount of energy that is needed is referred to as the boiling point of this particular substance. Then melting point, if you are to use melting point, then you're looking at the amount of energy that is needed to break into the solid lattice. So you've got this nice arrangement, okay, structure with this nice arrangement. Then for you to distort this arrangement, the amount of energy that is needed is referred to as the melting point of that particular substance. Then other parameters that might also be considered are parameters such as the triangle that you see there is a Greek symbol called delta. So delta means change in. Then the H that is shown here in a slanted form is called enthalpy. So this concept, I'm sure, was reviewed when you are looking at when you are learning chemistry back in secondary school. Enthalpy. So enthalpy refers to the heat content of a system. How much heat energy is present in a given system is referred to as the enthalpy. Okay, so now the change in enthalpy between when the reaction is starting and when it will have concluded, you want to try and establish how much heat energy would have been invested into the system, or how much of it would have been harvested out of that particular system. This is what this is basically about. So the enthalpy of vaporization, for instance, can also be used as one of the parameters that might try and explain the strength of the intermolecular forces that are existing amongst the molecules of a given substance. So what is this really? Enthalpy of the enthalpy, the enthalpy change of the change in enthalpy of vaporization is the amount of energy in kilojoules that is needed to change the state of a substance from a liquid to a gas. So the change in enthalpy of vaporization is the energy in kilojoules that is needed to change the state of a substance from a liquid to a gas. You can also use change in enthalpy of fusion. So the change in enthalpy of fusion can also be used as an indicator to try and determine the strength of the intermolecular forces that are existing amongst the molecules of a given substance. So what is change in enthalpy of fusion? The change in enthalpy of fusion is the amount of energy that is needed for you to change the state of a substance from solid to a liquid. Okay. Then you have the last one, which is the change in enthalpy of sublimation. The change in enthalpy of sublimation of a substance is the energy in kilojoules that is needed for you to change the state of a substance from solid to a gas. So all these parameters that we have talked about here can be used to determine the strength of the intermolecular forces in a given compound. Okay, so with that in mind, then we notice that the generalization that we're going to come up with would be that when you compare the intermolecular forces and the intramolecular forces, the intermolecular forces are much weaker compared to the intramolecular forces, and I hope everything that we have talked about is clear enough for us to be able to explain to someone who may be looking for this particular information, or for you to be able to answer questions in a quiz, the exam. Okay, just a minute. colleagues trying to join in. So we go to the next slide here. So this particular slide here brings in another type of interaction that we have. So the dipole-dipole interaction. So the dipole-dipole interactions, if you wanted to define this, you would say these are the attractive forces between polar molecules. So remember the aspect of polarization. If we had an atom A and an atom B connected together, and we have electrons concentrated on one side, we are going to have a structure where one part ends up with a positive charge, the other part ends up with a negative charge. So the part where there's a negative charge, that's where the electron density is higher and the electron density is lower here. So when these molecules orient themselves in such a way that the positively charged part of the molecule faces the negatively charged particle of the molecule, then you're going to have this arrangement almost everywhere within the structure, such that if we were to extend this idea to a substance that is polar and exists in a liquid, in a solid state, okay, the orientation is going to be such that the parts that are positively charged, will orient themselves closer to those that are negatively charged. Then you have this pattern repeated almost everywhere. You know, there's this orderly plus minus plus minus plus minus arrangement within the structure, and this arrangement that you see here helps us to explain why you know, polar solids have got defined structures. So already we are starting to see that we can use these forces to try and explain why certain substances have got the shapes that they do have, and others may not have exactly the same types of shapes. Okay. So another interaction that we have is the ion dipole force of interaction. So the ion dipole force of interaction, you would do well to remember this as the force of attraction, that exists between, you know, you have polar, I mean, for the ion dipole interaction, you're looking at the force of attraction that exists between an ion and a polar substance. But of course, this is also extended to the interactions that exist when you've got an ion and just any substance. So you will have this type of interaction. So in this particular case, we've got an interaction between an ion and a polar substance. So the orientation is going to be such that the polar substance will have its negatively charged part of, you know, the molecule oriented closer to the cation. And if you had a negatively charged particle interacting with the polar substance, then you'll have the positively charged part of the polar substance orienting itself closer to the an ion, that is a negatively charged particle. Okay. We now want to try and explain why some substances dissolve more or better in water than others. In this case, in this slide, we have two particles, both of which are cations, that is the sodium ion and the magnesium ion. Okay, so for those of you, I'm not sure if it is this group because you guys are so many. We've got the CHE 1000 students, you have the CHE 1010 students, and I'm teaching both groupings, and on top of that there are second years, there are third years, there are fourth years also. So I think one of the groups, it should be those from 1010 if I'm not mistaken. I taught them atomic structure, I taught them periodicity, and I taught them chemical bonding. So in periodicity, we looked at you know, guidelines that were supposed to be used for you to be able to arrange these species in their orders of increasing sizes and decreasing sizes. And there was a concept that I had emphasized on to your friends that they needed to look at, that the concept of effective nuclear charges. So we would use that particular concept to try and predict the sizes of these particles. So when you look at the diagram that we have here, when you look at these two, the way they're interacting with water, this interaction is said to be weak, the other interaction is said to be stronger. So we want to try and explain why this is so. So the explanation that you are going to have to give would be in relation to a concept that we refer to as charge density. So we have a concept that we refer to as charge density. So this charge density, is equal to the magnitude of charge. So magnitude of charge of particle, this can be positive particle or negative particle. Then you're going to divide by the size particle in question. Okay, so the size of the particles. So this ratio can be used to explain the reason that this one does not interact with water as much as this one does. So when you use the concept that I talked about of effective nuclear charge, you're looking at there's the aspect of shielding and how much pull would come from the nucleus. So when you look at the neutral atom for sodium, sodium has got one electron in the outermost shell. So when this particular uh, electron is lost, the shielding is not going to be lost as much. Okay, there's some effect that is coming from the nucleus, but the remaining electrons would still try to resist that pull that is coming from the nucleus to some extent, and therefore the electron does not, I mean the remaining structure with the remaining electrons in the outermost shell will not contract as much. But when you look at the neutral atom of magnesium, it has two electrons in the outermost shell. So when those two electrons are lost, there is going to be a bigger loss in terms of the shielding that was being offered to the electrons that are remaining. So the pull from the nucleus is going to be much greater, and therefore that is going to cause the atom to contract. That is why the cation of magnesium is smaller compared to the cation of sodium. So when you use the charge here and the size of the atom, you compute the charge ratio, you see that you're going the charge ratio is going to be lower. So you have a low charge ratio. When you look at the size of the magnesium ion compared to the magnitude of the magnitude of the charge and the size itself, the charge ratio that you're going to get would be high. Okay, so this you would do well to remember that the higher the charge density on a given particle, the greater its interaction is going to be with the water molecules, or the higher the solubility. So the higher the charge density, the higher the solubility. So the explanation is that magnesium ions have got a higher charge density compared to sodium ions, and therefore they have a greater uh, interaction with the water molecules, making them to be more soluble or being able to dissolve to a greater extent compared to the sodium ions. And I hope that was clear enough, and we should be able to answer questions that are given. So with that, then we can move to the next slide. So this particular slide brings in another dimension to everything that we have been trying to talk about. So here we want to try and explain what this is the induced dipole. So this particular induced dipole forms one explanation that you can give. You look at the structure of an atom. It's got a nucleus, it's got this region, which is referred to as where you have the energy levels. Okay, this entire region here there is an equal chance of you finding an electron there, an electron there, and an electron there. We were told that electrons exist in energy levels. Okay, these energy levels, we've got orbitals, the s orbital, the p orbital, the d orbital, all those orbitals that you talked about, and their respective capacities in terms of the number of electrons that you're likely to find in any of those. So even in each of those orbitals, the electrons are not stationary. You are not going to point to say, well, one of the electrons is seated there or stationed there. No, these electrons are moving the entire time. So what you get to have are just regions where the probability of you finding an electron becomes higher. So if the probability of all the electrons being found in this region is going to be the highest compared to there, then you are likely to have, because these electrons are spinning, so your electrons may drift and find themselves bunched up into some region. So that region where there are more electrons, that region is going to be said to have a higher electron density, and it will end up assuming a negative charge. So if that is the case, then the region where there is a deficiency in electrons becomes by definition a positively charged region. And if there is any particle that has got a charge on it, such as in this case we've got a cation with a positive charge, there's going to be an interaction. But this interaction just forms within a very short period of time, within a split second. So this forms within a split second. Okay, so it is going to be there one moment, the next moment it is not there. So it is an on-off, on-off, on-off kind of arrangement, because once the electrons decide to shift to a different region, then this part that was negative charge might become positive charge, and if that is the case, then there's going to be some repulsion. So it just keeps on forming and disappearing and forming and disappearing. And um, another way of looking at this is, because this one is positively charged, it may attract the electrons to come closer to it, then you're going to have the other region being positively charged, because the two positive charges cannot be on the same region. So this particular form of dipole is called an induced dipole. And when you've got an ion interacting with a non-polar molecule, there will be an ion-induced interaction. If you have a polar substance, then you're going to have a dipole-induced dipole interaction. Okay, because we've got this one is a dipole itself. It's a polar substance, so it's a dipole-induced dipole interaction that you're going to have. Okay, so with that in mind, then, how would you explain the fact that particles of a non-polar substance are still able to hold on to one another? So how are they able to hold on to one another? They are able to coexist, okay, and yet they don't have any charges whatsoever in them. So using this idea that I explained to you of electrons spinning, we can try to extend this to the next slide that we're going to have. So a question might be asked, explain with the use of a diagram or an illustration how London dispersion forces form. So these forces that we talked about here, I forgot to mention one very important thing. These dispersion forces can also be referred to as London dispersion forces. So with the use of a diagram, explain how London dispersion forces come about in a non-polar substance amongst its molecules. So when you have got electrons spinning in one of these molecules or atoms of this particular substance, the electrons can decide to group themselves on, or just coincidentally, they may group themselves in one region. And if that happens, that region becomes negatively charged because there is a higher electron density in that region. The other one becomes negatively charged. So if there is another particle nearby, that can induce a formation of a positive charge on that end where the negative charge is on this particular particle, because the negative charge is going to push the electrons towards the other side. So if that happens in the next molecule or atom, that might induce formation of a positive charge closer to it, and that if there is another particle that has a negative charge in it, that particle might be pushed away. There is some repulsion that might result. So this arrangement is going to continue such that when you look at the particles, one moment, the next moment, the orientations are going to change. The next moment, the orientations are going to change, and they keep changing and changing and changing. And because the electrons are spinning, they are not stationary, this behavior is going to go on, perpetually. They will just keep changing their orientations from, time to time and time to time and time again. So this behavior may be used to try and explain why matter, which is made up of tiny particles, these particles are in constant random motion. Imagine that these particles were particles of a liquid. They cannot be in the same location. This particle cannot be in the same location, because even when it behaves like that, if there's another particle that behaves in the same manner and the positive charge is closer to this particle will be pushed away from that particle because there would be repulsion. So the particles are attracting one another, pushing one another away from themselves. They are repelling one another. They are attracting one another just like that, and this goes on and on and on, and you have this fitting into the definition that matter is made up of tiny particles that are in a constant random motion. Okay. So with that in mind, then we try and look at another type of force, which is a special type of dipole interaction called hydrogen bonding. So what is this force of attraction? So this particular force of attraction is the special dipole interaction, and it takes place when you have a hydrogen atom uh, uh, in a polar bond. A polar bond may be a nitrogen-hydrogen, oxygen-hydrogen, or fluorine-hydrogen bond, and there should be an interaction with an electronegative atom, such as oxygen, you have nitrogen or fluorine. So with the use of a diagram, explain how hydrogen bonding forms takes place. So if you had two molecules of water, remember the arrangement of atoms in water molecule. So you have, this is partially positively charged, this is partially positively charged, partially positively charged, partially positively charged, and partially negatively charged. But there are lone pairs of electrons on this oxygen atom. Okay, so the lone pairs of electrons on the oxygen atom on one of the water molecules can be used to form an interaction between this water molecule and the next water molecule. So the lone pairs of electrons creates an interaction with the positively charged atom of the next water molecule. When you look at the molecules of ammonia themselves, they can also interact through hydrogen bonding. The lone pairs of electrons on one atom of nitrogen can create an interaction with the next molecule using the positively charged hydrogen atom of this particular molecule. The same thing can happen when you have the lone pairs of electrons of hydrogen on the water molecule interacting with the partially positively charged atom of the nitrogen molecule. The electrons on ammonia can interact with water molecules. The lone pairs of electrons on fluorine in hydrogen fluoride can interact with the hydrogen atoms of ammonia, and the trend just goes on like that. Okay, so this is the way hydrogen bonding comes about. So let us try and answer this question together. I'll guide us through in terms of the choices that I came up with for you guys. So you have those options. So the first option is dimethyl ether. So dimethyl ether, you've got compounds that we called ether when you're looking at your basic organic chemistry in secondary school. So ethers are compounds that have got an alkyl group on one side connected to the other side through oxygen. So either of these, in this case, we have methyl groups in this example. So that's a methyl group, that's a methyl group, and then you've got a dimethyl ether. So dimethyl ether has got an oxygen with two lone pairs of electrons. So either of these two lone pairs of electrons can be used to form an interaction with the hydrogen atom of the water molecule. Okay. The next option that we have is the fluoride ion. So the fluoride ion initially had three pairs of lone pairs of electrons, that is. So and it has gained an extra electron. So any of the four pairs of electrons that we now have can be used to create an interaction between the fluoride ion and the water molecule. So this is straightforward. But you do well to notice that the fluoride, the fluorine atom rather, in its free state can form these interactions that we are seeing here, these ones here. The only time that fluorine will not be able to interact with the water molecules would be when you have this molecule. Okay. This particular molecule is not able to donate electrons, it's not able to accept electrons. So we should be able to differentiate between or amongst these three scenarios that we have: the ion, the free fluorine atom, and the molecule. Okay, I had a question that was asked by one of your friends, and there was a confusion as to which one really should be excluded. So it is this particular one here. Okay, so either of these two. So when you talk about fluorine in its free state, when it is not bonded to the other, because this one exists as a molecule. So as a molecule, no hydrogen bonding. When it is isolated, in which case it is not able to actually even exist in this form, because it can easily abstract an electron and then it forms this, which is much more stable compared to the other one. Then when you look at the third option that we went for, which is formic acid, which is methanoic acid, in other words. So methanoic acid has a functional group called carboxyl group here. This carboxyl group has two oxygen atoms. One oxygen atom is bonded to carbon through a double bond. The other one is bonded to carbon through a single bond. So the lone pairs of electrons on the oxygen atom that is doubly bonded to carbon, we can create an interaction with a water molecule through formation of a hydrogen bond. For the hydrogen atom that is connected to the oxygen atom that is connected to the carbon atom through a single bond, an interaction can still occur. And this time around, we are going to have two we have two pairs of lone pairs of electrons on the water molecule, either of which can be used to form that interaction there. But what is interesting is we see that these two are not participating in terms of the choices that we came up with. But why have we not picked any of those two that are remaining? So we also want to establish why that is the case. So we see that when you look at what is the, let me just remove this. When we look at the structure of methane, it has those hydrogens attached to it. Okay. We see that all the electrons that are present in this particular structure are participating in bond formation. There are no lone pairs of electrons on the carbon atom. There are no lone pairs of electrons on any of the hydrogen atoms. So one reason that you're going to give, we can design a question where we ask you the very exact question, then we pick those choices for you. We tell you to say, amongst these molecules that we have, the ones that would form hydrogen bonds are dimethyl ether, the fluoride ion, and formic acid. Explain why methane and sodium ion are not able to form hydrogen bonds. So the explanation that you'll give is this: that in this particular structure, there are no lone pairs of electrons, so no hydrogen bonding. The other explanation will be that carbon is not electronegative enough for it to interact with it, either the oxygen atom of the water molecule or the hydrogen atom of the water molecule. That is another explanation that you would have to give. Then for the sodium ion, this one uh, has got a permanent, it has got a permanent charge, okay, and it is an ion, so no interactions would exist when you look at it. Okay, so I thought that we could go through these together, and besides, remember the what is the interaction that we talked about before? I forget this one, the ion dipole interaction. So this is the only interaction that is going to form when you look at sodium ion and water. Like you, so you've got the ion dipole interaction, which we said was the type of interaction that would form when you've got an ion and any type of molecule. So therefore, the only choices that we have are a dimethyl ether, the fluoride ions, and formic acid as the only ones that should be able to form hydrogen bonds. Okay. I have another session that I, yes, yes.
Sorry, just before we end the class, what did you say on the sodium ion? Why it cannot bond
Okay,
with
I don't know. Wait. I don't know if you're using two gadgets. So there is some echo of some sort, which is making it very difficult for me to get what you are saying exactly. If you have got two gadgets, try to mute one gadget, then you speak through only one, so that we avoid that echo.
Okay. I was in pods. I was saying, sir, what did you say on the last one? The sodium ion, why it cannot bond with water?
So the reason that sodium ion does not bond with water to form hydrogen bonds. So ions don't form hydrogen bonds, in other words. So the sodium ion forms ion dipole bonds interactions with the water's oxygen. Okay, so ions don't form uh, hydrogen bonds. Remember the condition that we had set for formation of hydrogen bonds. So the a compound with which this hydrogen bond should form, it should have, we should have atoms such as this one, fluorine. We should have oxygen or, you know, nitrogen. So nitrogen should be bonded to this particular compound directly. If that happens, then you are going to have formation of hydrogen bonds with water molecules. Okay, so that is the explanation that you're going to give. You're going to say ions do not form hydrogen bonds. The only interactions that you're going to have would be the ion dipole forces that are going to form. And this one having a full charge on it, this is very possible that that is going to be the only interaction that is going to be there. Okay, so
Thank
we
you, sir.
okay, sure. We call it a day. Let me attend to your friends also. There is another group that I still have to, attend to. So thank you so much, you guys, for finding time to join in. Let's keep doing this and make sure that we learn everything that needs learning for you, people to be able to